Okay, so let's come back and actually show you how you can use this technology for some phenomenological stuff. And I want to do that by generalizing our discussion slightly away from masses towards just a general operator product expansion. So everything that we've said here for masses can be applied more generally to an operator product expansion. So let me show you what I mean. So let's first consider what I mean by an operator product expansion in MSbar. So you can think of this like maybe I'm integrating out a heavy particle, and I'm writing a formula down, and it has some Wilson coefficients, it has some operators, and it's a Taylor series in this parameter Q, which is the hard scale, high energy scale. And I'm basically just expanding, if you like, in lambda QCD over Q. And the operators, they're set by lambda QCD. So I'm going to take this guy to be dimensionless. This is some dimensionless observable. Okay, you can always make it dimensionless by suitably choosing, multiplying by appropriate mass scales. So then this here will be a dimensionless Wilson coefficient. And it's a Wilson coefficient in MSbar. That's what the bar means. And so this is an MSbar operator, MSbar matrix element of some operator. And it's also dimensionless. So this guy will be dimensionless too. And finally, this guy will have dimension equals 1. Now in MSbar, what's beautiful about MSbar is that the series for these coefficients are very simple. That's why people like to compute in MSbar. So if you look at what the series for C bar looks like, the form of it is as follows. It's got dependence on mu over q, and then alpha s of mu. And these guys here are not an arbitrary function of mu over q, but they're really just some logs. So this looks like a series of logs. So in MSbar, you're only seeing these logarithms. So that's good from a computational point of view, but we also know that generically in this MSbar approach, you might get sensitivity to Renormalons. It's also, another thing we like about MSbar is that it satisfies all the symmetries we want to keep. It doesn't mess them up, so it's Lorentz and gauge invariant, which is always a good thing. And not only is it simple for multi-loop computations, but multi-loop computations are not even done in other schemes because they're just too difficult. So it really makes multi-loop computations possible. And the bot, there's only really this one bot that has this Renormalon issue. So we talked about Renormalon for a mass, and I just showed you what it was, and then we explored it. Here, let me tell you what the Renormalon would be. So generically, what the Renormalon would be is the following. You would have an ambiguity in the coefficient C0 bar. It's of the size lambda QCD over m over whatever the scale Q is. And you would have the same ambiguity in this theta 1 bar. So this theta 1 bar, which is an MSbar matrix element, has an ambiguity, which is of order lambda QCD. This guy has an ambiguity, and those ambiguities cancel. So you're dividing up the physics again in MSbar into short distance physics and long distance physics. And the interesting thing is that it's there's a piece of long distance physics trapped in the C0 that should be, if you really wanted it, should be physically in the theta 1 bar and vice versa. So, so you really, what's the problem with MSbar is that there's a piece of something that you want in theta 1 bar but ends up just being in the C0 bar. And that's what I mean by this, that there's something here which is infrared sensitive. Correspondingly, there's kind of a ultraviolet sensitivity in this theta 1 bar, and you'd like to get that rearranged in an appropriate way, and that's like this kind of rearrangement we were making by changing schemes for masses, except here it's going to be changing schemes for Wilson coefficients. So this thing here is what we would call a U equals 1 Renormalon. So what happens with U equals 1 is that you make a connection between the leading order term and the power suppressed term. That's what happens with the delta C0 bar. So in order to flesh out a little bit better what I just said in words, let's pretend that we understand what the theory is, and let's just pretend it's some integral. And I'll just show you what is going on here. So let's imagine that our theory is an integral. Instead of a quantum theory, it's a one-dimensional integral. And it has two scales. One which I'll call lambda QCD, which is some low scale, and one which I'll call Q, which is some high scale. And I'm using a notation where the integral could diverge, and I regulate it with a dimensional regularization type parameter. So I'm doing a one-dimensional integral, but continuing into epsilon dimensions to regulate any divergences. So what MSbar does with this integral is it just says, well, I'm not going to change the limits of the integral. I'm just going to either expand out this f or expand out this denominator. I'll do two different Taylor series, and then I'll put them together. And that's basically, well, how I'm identifying the terms in my OPE. So MSbar. So I sort of associate there being a high energy piece where K is of order Q, and then there's some low energy piece. I don't change the limits. So in the low energy piece, I keep the full function f, and then I expand out the other thing. And if I drop the dots in this formula, I can identify these integrals as toy models for the things that are appearing in my OPE. So let me write that OPE again. So here these things are 1, this example. This integral here, which is over high energy scales K dominated by Q, is this guy. And this integral here, where K is of order lambda QCD, effectively, there's a 1 over Q, which is this 1 over Q. That's giving me the operator, theta 1 bar. Okay? So Wilson coefficient is the high energy piece of the original thing. Matrix element here is the low energy piece, which is suppressed by 1 over Q. Okay? But they both came from the same physics in the beginning. And I just was expanding it because that's how I wanted to organize it. Now, the thing about MSbar is that you integrate all the way down to 0 there, and you integrate all the way up to infinity here. Okay, and that's where the Renormalon problems come from. So this little procedure here separates the long and short distance physics for the logs. It does that correctly. But for powers, we effectively rely on the fact that it sets scaleless integrals to 0. That's what's forced upon us by the definition of MSbar and a dimensional regularization. And what goes wrong is basically that physically we're still integrating over regions of those integrals which are not associated to the physics that should be in those parameters. Okay, so now this is a toy example, but the same thing is happening in the quantum field theory. When you think about what you're doing when you write down Feynman diagrams and you construct a Wilson coefficient, it's effectively the same thing. In dimensional regularization, you're integrating over all values of the momentum, and this little kind of toy analogy is actually apt for what's going on in a true operator product expansion. What would happen if you did a Wilsonian picture in our toy model? Well, then you would cut off the integrals explicitly. You'd say, let's introduce some scale lambda f. I could still think of expanding in the same way. I don't need the dimensional regularization anymore, so I'll set that, get rid of that. I think of breaking the integral into two pieces, the low energy and high energy pieces. And in each of those pieces, I expand the integral in different ways. So the same type of expansion, I'm just regulating it differently. Now I'm guaranteed that this is high energy and this is low energy. And you could write down sort of what this is a proxy for as a Wilsonian OPE. Mu gets replaced by this scale lambda f. Everything gets a W for Wilsonian. So again, this is one with our toy model. This guy is this guy now. This guy is this guy now. So it's a very similar kind of association, but just the way that we're treating the integral is different. And this way of doing things, you don't have any problem with the Renormalon. You just have an explicit cutoff, which says there's no low energy thing in part of this, and there's no high energy part of that. I'm not integrating all the way down to 0 in the first integral, so I don't have any problems with the Renormalon. The Renormalon came from infrared physics that was happening near k equals 0. And in this one, there's no sort of problem which would come from infinity. So in some sense, this is what we'd like to do. And the but here is that it causes difficulties with symmetries. In particular, it generically breaks gauge invariance and Lorentz invariance. Let's get broken. And the calculations that you would like to do are just too difficult. I don't know of anybody that's done it. Maybe somebody's done 2 loops in the Wilsonian picture, but nobody's ever done 3. Okay, so you have, in some sense, you have some nice things here, you have some nice things here, but they're not the same nice things, and you'd like to have something that does the best of both. And that's effectively what we're doing when we construct these R schemes. What we're doing is we're saying, well, let's take MSbar as a starting point and try to get rid of the problem that it has by perturbing towards a Wilsonian picture. So what would an R scheme OPE look like? Start with MSbar and make a scheme change. I make a scheme change here both to the operators and to the, I make the same scheme change to the coefficients. So I'm just really moving things around. So let me just formally write down what such a scheme change would look like. I set up some coefficients, Pn, and I make the same, I do a subtraction on the operators and an addition on the coefficients in the way I've written it. So that's just a rearrangement of the physics, and we've set it up so that the result of that looks like this. I took, in this example, C1 equal to 1 for simplicity. It's a little more complicated if I want to keep it, but we could keep it if we needed to. So basically, I've made a rearrangement to some equivalent OPE by just changing the thing, the definitions here. But I have now the freedom to pick these Ds, and what I can do is I can pick the Ds to have the same Renormalon as the MSbar scheme, and therefore I can iteratively again remove the first problematic term of this to get a better defined theta 1 and C0, just like we were doing for the masses. So you can remove the U equals 1, for example. You can remove the U equals 1 Renormalon by choosing the D. And that's exactly what the Wilsonian was trying to do for you. And that's what it was doing for you with putting this cutoff. MSbar was having problems at 0, and we're sort of perturbatively removing those problems, perturbatively going towards the Wilsonian picture. And the nice thing about this is that we can maintain the symmetries, still gauge invariant, still Lorentz invariant. And we don't get the full sort of power of the Wilsonian, but we get closer to it. And we can, in some sense, get as close as we want, again, by sort of perturbing us from order by order. So what we introduce is power law dependence in R. And that power law dependence is like the power law, it's the analog of the power law dependence that would be in the Wilsonian scheme. So when you have integrals like this, you would have powers. There's nothing that stops you from having a complicated function of q over lambda. And what we're saying is that the dominant kind of power law sensitive terms here and here are captured by making this scheme change. So we decide that we like MSbar because we have calculations that other people have done, hopefully. After three-loop order, you certainly hope that someone else spent 2 years of their life on it rather than you. And you can take and perturb your results from MSbar towards a gauge invariant, Lorentz invariant version of Wilsonian, of the Wilsonian picture. So let me give you one example of that to show you in practice, putting in some numbers. Oh, I'm not quite there yet. OK, so let me give you a well-defined scheme, which is analogous to the scheme that we just talked about, which was MSR scheme for the mass. There's also an MSR scheme for the OPE. And again, the attitude is, let's not calculate anything new that we don't have to. So we'll reuse the coefficients of MSbar. Those coefficients had the Renormalon. So if those coefficients were, we called them a few minutes ago, Bn mu over q, we just reuse these at a different scale. So what we do is we say dn of mu over r is defined to be the Bn of mu over r. So these guys were the MSbar coefficients. These guys are whatever we decide to put into the series over there. Just take them to be equal. That's the MSR scheme. And then if you look at what the coefficient is, if we just write out explicitly what the coefficient is by plugging in the series, you can again see the kind of how it's providing a cutoff. So this was our original MSbar series, Bn of mu over q. We introduced a subtraction, which is suppressed by r over q times the same series Bn. And this r is providing kind of like a power law cutoff on a problem that this guy had. Exactly a power law cutoff. So again, if you look at the Renormalon in this thing, this combined thing, the Renormalon is independent of r and q. When you say you would just plug in the bubble series result, you'd find actually that the r over q here would cancel out. And so these would just exactly cancel each other. U equals 1 Renormalon. And again, if I wanted to probe other Renormalons, I'd have to consider other powers besides r over q. But those actually in this OPE would be connected to other operators. So there's other subleading Renormalons here, which could be connected to 1 over q squared, et cetera, et cetera. And in MSbar, that generically will happen. But usually, it suffices just to worry about the first one, since many people in the community that do these multi-loop calculations don't even worry about the first one. Anyway. OK, so you can, again, after you've got this definition, you could actually formally write this as C0 bar of q comma mu, if you want to think about what it is, minus r over q, same Wilson coefficient, replacing all the q's by r. Okay, so that's another way of saying what the scheme change is from MSbar results to this result. And this r is acting like an IR cutoff to get rid of the bad problem. And again, we have a renormalization group. So r d by dr of this Wilson coefficient. It's convenient to think about that renormalization group with the log cutoff mu set equal to the power law cutoff r. And it's very much like our masses. There's some function with an r in front, and we could formally write down solutions to it. And we can explicitly plug in results, given how many terms in the series we know in the MSbar series. So all the anomalous dimensions of this Wilson coefficient would be determined by the MSbar series, the original one, because the scheme that we're defining is set up so that it uses those MSbar coefficients. So what would the RG look like? It's the same kind of structure as what we had for masses. Some gamma functions. And you can think of this as some C0. If you want kind of to have a more standard notation, you would say that this is some U function. And this is a bit of abusive notation actually here because it's additive, not multiplicative. But if you allow me to put this guy into here, then I can always write it this way. And I'll just do that for convenience.